Hey Chemistry, Mrs. KJ here, going over lesson 1.13, Some Properties of Solids, for second semester core chemistry. The particles that make up a solid do not move much, but of course, they still move. And of course, the solid retains its shape. In 2004, astronomers at the Harvard Smithsonian Center for Astrophysics announced that they had discovered a diamond star. The diamond was formed from the carbon-oxygen core of a dying white dwarf star. The diamond is a typical example of a solid and has properties similar to other solids, such as sugar and table salt. Here, you will learn the structures and properties of solids and how they can be explained by intermolecular forces. Solid properties, very strong intermolecular forces. They have a definite shape and a definite volume. They are not compressible and they are not fluid. So, describe the atomic or molecular structure of liquids and solids. Contrast the intermolecular forces of atoms and molecules in a liquid with those of a solid. Given examples of crystalline solids, describe their properties and bonding patterns. And make sure you write down these vocab words. Allotrope is one of the structural forms of a pure solid. Amorphous solid is a solid that lacks a regular internal molecular structure. So look at the word morph. What does morph mean? Like a morphling. Morph means that it can change. So think of things that are like ooey and gooey for this. And a unit cell. In crystals, an arrangement of atoms or ions in a particular geometric shape. And of course, we'll talk more about those. Of course, you can log into the lesson and download the student guide if you'd like it. This stylized cutaway illustration, so in other words, someone drew it, shows a diamond interior for a white dwarf. How crazy is that? It's a star. Think of how huge they are, and it's a solid diamond. Astronomers discovered a diamond star 50 light years away. In 2004, astronomers Travis Metcalf and Ruth Bazinet at the Harvard Smithsonian Center for Astrophysics announced the discovery of a diamond star 50 light years from Earth in the constellation Centaurus. The star BPM 37093, called Lucy after the Beatles' song Lucy in the Sky with Diamonds, is a diamond white, dying white dwarf star. As the star died, the immense temperature and pressure in the star's core forced carbon atoms and oxygen atoms so close together that they fused and crystallized as the star cooled. The result is a huge diamond of about 1 times 10 to the 34th carats. The largest diamond on Earth is 530 carats. So take a 1 and write 34 zeros after it, and that's how many carats it is. It's crazy, crazy huge. So, how do solids compare with liquids and gases? In gases, molecules are far apart and they move rapidly and randomly throughout their container, colliding with one another and with the walls of the container. In liquids, the molecules are much closer together, but still a little far apart. They contact, they slide, they flow around one another, they vibrate and move from place to place. In solids, the molecules are in contact with one another, but they do not move from place to place. So, yes, they still move and vibrate, but they stay where they are. It's not like water where, the water molecule in liquid is up at the top in the glass, and then it's in the middle, and then it's at the bottom, and then it's on the left, and it's on the right. No. Okay, if you have a molecule of ice, the top right corner of the block of ice, those molecules, they stay there because they are held rigidly and they can only vibrate. What holds the molecules of a solid together? The molecules of any substance have kinetic energy, meaning energy of motion. Molecules are also affected by intermolecular forces. So remember, that's the force between one molecule and another molecule, like what makes water line up. What ultimately determines the phase of the substance is how the strength of the intermolecular force compares to the kinetic energy of the molecules. In solids, the strength of the intermolecular forces far outweigh the internal kinetic energy of the atoms or molecules. So in other words, it's barely moving, it's just vibrating back and forth, and they're right next to each other, and so there's a really strong attraction from molecule to molecule, which means a high intermolecular force. All right. So again, our gases are everywhere. Our molecules of liquid are moving slower. I know it doesn't show this well. I mean, these should be moving crazy fast. It looks like it's kind of right. So these are moving medium. These are vibrating. Because they're so close together, they're going to interact with each other. Like these are water molecules lining up really nice. That's because of the intermolecular forces. Strong intermolecular forces give solids definite volume and a variety of shapes. So salt is a crystalline solid because it is made of crystals that are all alike. Now, if you'd say, well, they're slightly different shapes, yeah, but these are huge chunks when you look at how small the atoms and molecules are. So you always have the NaCl, NaCl. They line up all nice and perfectly because of the positive and negatives. Since glass is a amorphous solid, it can flow and be shaped. Remember, we said morph means change. An amorphous solid, when we heat it, it's kind of like Laffy Taffy. Once cooled, the glass molecules remain in place. Strong intermolecular forces give solids definite volume and a variety of shapes. Intermolecular forces work over short distances. So in other words, they attract the molecules right next to them, not molecules on the other side of the room. Because the kinetic force of molecules is low, so they're moving slowly, the intermolecular forces are very strong because they're just sitting next to each other, so they have time and space to interact with each other. The solid molecules are tightly packed, giving them a definite volume. The solid molecules can be packed in a variety of ways, and as a result, solids have definite shapes. Make sure you have both these written down. Crystalline solids. The solid molecules are arranged in orderly, repeating patterns. Examples of crystallines are diamonds, gemstones, rocks, sugar, salt. So it's got a pattern to the molecules lining up. Amorphous solid. The solid molecules lack a regular internal structure. Amorphous solids are more like supercooled liquids, where the molecules have become permanently frozen. Examples include glass, plastic, a rubber band. So I just Googled crystalline versus amorphous. Crystalline, all nice and patterned. Non-crystalline, all over. Really nice pattern. No good pattern, amorphous. No good pattern, amorphous. Pretty pattern, crystalline. You get the idea. And you can see polycrystalline, but we're going to skip that for now. In your notes, I would draw a little example of crystalline, just so you know what we mean about lining up. And then maybe like a non-crystalline. Sometimes pictures help remember. Chemical bonds produce various crystalline types. The atoms within a crystal substance can be bound by ionic, covalent, or metallic bonds. So ionic means you have a metal and a nonmetal, a positive, negative. Covalent, two or more nonmetals sharing electrons, or metallic, metals. Each bond type produces crystals with different properties. There are four major types. Number one, ionic. Make sure you know all these. Atoms are metals bound to nonmetals. Ionic bonds are strong, such as those in table salts, magnesium oxide, and sodium fluoride. Covalent network. All atoms are strongly covalently bonded to one another, sharing electrons, as the carbon atoms in diamonds and the atoms of quartz, which is silicon dioxide. Metallic bonds form between metal cations and a sea of electrons. Remember, the electrons flow all over, which is why we can use them to conduct electricity. Examples, copper, gold, silver. Covalent molecular. Covalently bonded molecules are held together by intermolecular forces. One example is glucose or sugar. So, bond type, hardness, ionic, very hard, brittle, covalent network. Harder, brittle. Metallic, soft, malleable. Covalent, softer. Boiling points. Because it's so hard, they have a high boiling point. Because these are softer, they have a lower boiling point. Although metals vary a lot because there's so many metals. Conductivity. The only one that has good conductivity is your pure metals because of the sea of electrons. Crystal structures have various shapes. The simplest arrangement of atoms or molecules that retains the basic shape of a crystal is called the unit cell. All right, so this one shows like table salts. So you have the NaCl, NaCl. Look at that, NaCl. You can see the pattern. Unit cells are arranged in repeating structures called the crystal lattice. Make sure you write down crystal lattice. Crystal lattices can also be arranged in various ways to form the overall structure of the crystal. In a cubic unit cell, for example, all the angles are right angles and all the sides are of equal length. So in other words, it's like perfect cubes on top of each other. You can have different designs too, like hexagons, pentagons, and like that, but this is a really good one showing that, yep, it just does this 5 million times and then you get a crystal of salt. Crystalline solids of the same types have various forms called allotropes. Even crystals of the same substances can have different forms. These different forms are called allotropes. So remember, allotrope is one of the structural forms of pure solid. For example, carbon has many allotropes. Okay, so this is a fullerene. Have numerous applications, include superconducting salts and biological crystals. So let's look at that one first. Discovered in 1985, these molecules have 60 carbon atoms arranged in a hollow sphere, much like a soccer ball. Fullerenes, or buckyballs, named after architect R. Buckminster Fuller, form when vaporized carbon condenses in an inert gas environment such as helium. Here are the two you're used to seeing, diamonds and graphite. These are all made out of pure carbon. Because pure carbon can form different structures, those different structures are called allotropes. So diamond, each carbon is covalently bonded to 4 neighboring carbon atoms to form a rigid, hard structure, the hardest naturally occurring solid. Graphite, think about a pencil. You can scrape that off with your fingernail. Diamonds are the hardest thing on Earth. And graphite, also pure carbon, you can scrape with your fingernail. Carbons are arranged in hexagons, which in turn are arranged in flat sheets. The sheets can slide along each other, making graphite very soft. That's why we use it in what we call the lead, pencil lead, because the sheets just slide off onto your paper. So here we have a diamond structure. Here we have graphite. You can see how it's like there's sheets, there's layers of hexagons on top of each other. So again, carbon, but very different than a buckyball as well, which is 60 carbons making a big soccer ball-like sphere. Strong intermolecular forces and sparse intermolecular spaces, meaning they're really close together, limit movement of solids. So a salt crystal really looks like that with all the sodium Na and chlorine Cl atoms lined up. Consider a crystal such as sodium chloride. As in any solid, the atoms are tightly packed with little or no space between them. The intermolecular forces are strong and limit the movement of atoms. Because there is no space between the atoms in the solid, solids are incompressible. You can't squeeze them together, and therefore retain their shape under most conditions. Extremely high pressures, such as hundreds or thousands of atmospheres, can change crystal shapes. Amorphous solids do not have a definite shape. Because glass is amorphous, it can be shaped in any number of ways, then cooled or frozen into place. So amorphous structure that lacks a regular internal molecular structure. So you don't have these nice definite patterns of lining up. When a substance cools into amorphous solids, they retain fluid-like properties and cool into a rigid form. As such, they can be manipulated into any desired shape. For example, glass can be formed into a flat window, a bottle, or an intricate sculpture. When glass breaks, it does not break into definite identical shapes like a crystal, but rather into randomly shaped fragments. The ability of amorphous solids to be molded makes them very useful. Another example is rubber, which is found in automobile tires and gaskets. Plastics are also amorphous solids that can be molded into many shapes and sizes. Solids have the properties very strong intermolecular forces, definite shape and volume, not compressible, not fluid. Solids are the most prominent low temperature phase. Solids have definite shape and volume. The strength of intermolecular forces, if the molecules of solids far outweighs the kinetic energy. Remember, they're moving really slow, so they have really, really high intermolecular forces. Intermolecular forces hold solid molecules rigidly together with little or no space, and the kinetic energy is so low that the molecules can only vibrate. Solids form either crystals or amorphous solids. The types and strengths of bonds within crystals determine their types and properties. Crystals have unit cells that repeat to form the crystal lattice. Unit cells of various crystal shapes differ in their relative lengths of the sides and of the angles where the sides meet. Crystals of the same solid may have allotropes, so like diamonds and graphite are both forms of carbon, and the buckyballs. In other words, different forms with different properties. Okay, and again, I just want to remind you, make sure that you know this chart. Where is it? Where is it? I'm going to run out of time. There it is. All right, make sure you know about these different ones. These should all be reviewed except for possibly covalent network, so make sure that you check those over. All right, if you have questions, let me know. Bye.